So in this lecture, we'll talk about partial Fourier acquisitions and partial Fourier and reconstruction of images from partial Fourier K-space. This is part 2 of this discussion, where in the first part we talked about 3 methods for reconstructing partial Fourier images, including zero filling, that is just doing nothing, phase correction and conjugate synthesis, where we remove the low resolution phase from the image and then synthesize the missing K-space data, and then homodyne reconstruction, where we fix the weighting in K-space that is applied by the fix the weighting, the non-uniform weighting of K-space that is applied by the partial Fourier acquisition. The direct methods, PCCS and homodyne, have problems due to the interaction of phase correction, the phase correction step, with the conjugate synthesis step, that is the synthesis of the missing K-space data. So, for example, in phase-corrected conjugate synthesis, the phase correction blurs the edge of the K-space data, resulting in transients that shouldn't be there. So that is what I'm illustrating here is the support, the hard edge here represents the support of the collected data, where we have collected data versus not. And then what we're doing here is in phase-corrected conjugate synthesis is we take the low-resolution image phase that we get from the symmetrically sampled region of K-space. We multiply the image by the complex conjugate of that to try to remove all the image phase, and then we go back to K-space to fill in the data. Problem with that is that when we do that multiplication in the image domain, we have convolved the image, the collected data with a narrow point spread function here in the K-space domain, and that causes these ripples near that edge. And then when we do the conjugate synthesis, that is when we then copy the acquired asymmetric data to the unacquired region, we end up with this modulation of the data. So the original near where the transient near where the edge was, so the original data then is distorted by that phase correction. And this is what I mean when I say that these two steps have interacted with each other, right? So when we apply the phase correction, that induces these transients, and then they further interact with the signal after synthesizing the missing data. Now, if you note from that previous example, we actually get ripples in data that we have actually collected, right? So we've actually sort of hurt to the data that we had. So ideally, we could reconstruct an image that satisfies 2 conditions. First, that its discrete Fourier transform matches the collected partial Fourier data exactly, right? That is, we trust the data we have. We shouldn't be changing it when we're doing the partial Fourier reconstruction. The other thing it should satisfy is that its phase should match that of the low resolution or symmetrically sampled estimate. So we think that the low resolution symmetrically sampled estimate of the phase is accurate. So that should be the phase of the image. So note that before, what we were trying to do was remove all the image phase. What we're going to do here is actually keep it. And why do we want it here? Well, because we can't. The reason is that we can't expect a zero phase image to match the original data exactly when that data corresponds to an image that we know has non-zero phase. So we're actually going to preserve the phase now, but just require it to be equal to the phase of the symmetrically sampled region, the image corresponding to the symmetrically sampled region. So we want it here because we can't expect a zero phase image to match the original data exactly. That is, we can't expect a zero phase image to satisfy condition 1 above. So, sorry, match original data exactly when we know that that image image data corresponds to an image with non-zero phase. So here we're actually going to preserve it. Okay, but how do we find an image like this? So what we're going to do here is use what's called a POX algorithm, which stands for projection onto convex sets. And it's a widely used algorithm. This acronym didn't come about in MR at all. It's a basic optimization method where you try to find the intersection of two sets of solutions. So POX algorithms pop up a lot in inverse problems and image reconstruction. So it's worth some, albeit high-level overview of what they are. So let's introduce them in the context of our partial Fourier reconstruction problem. In this context, we have two convex sets that we would like our solution, and we would like our solution to lie in both of them. The first set is the set of images with k-space data matching the acquired data. The set of images with k-space data matching the acquired data. And the second is the set of images with phase that's equal to the low-res phase. That's derived from the symmetrically sampled region. These are two sets, and we'd like our solution image to lie in both of these sets simultaneously. So to satisfy both, we want to find an image in the intersection of these two sets. So I've arbitrarily drawn one set as this oval here. This is like a set in two coordinates. And let's say that our initial point is up here, and it lies in just one of the sets. And we could arbitrarily say that set 1 is the set of images that have k-space data matching the acquired data, and that set 2 is arbitrarily the set of images with phase equal to the low-res phase. So the question then is, how do we find an image in the intersection of these two steps? Aside from definitions of the two sets we care about, the other ingredients we're going to need for this are projectors that take any given point, an arbitrary point, into each set, where a projector is a function. Again, a projector is a function that takes a point inside or out of that set and yields the point in the set that's closest in the Euclidean sense. So this is a function that takes a point that can be inside or outside that set and projects it to the point, and converts it or projects it to the point that is closest but in the set. In a Euclidean sense. Okay, so that is if you have this circular set here and you have an initial point x, the projector will just take it to the boundary, the closest point on the boundary. If x were lying inside the set, it would just stay put, given an ideal projector. So that is, given an initial point lying in one of the sets, we iteratively calculate projections of that point between sets, which will eventually yield a point in the intersection. You can show that if you keep doing this over and over again, taking the current point and projecting it to one set and then back to the other set and back and forth and back and forth and back and forth, the fact that you're always bringing it to the closest point in the other set means that eventually you'll get to a point in the intersection of the two sets, which in our context, in the context of our problem, is a point that satisfies both of our constraints, since our constraints are defined to sets. So here's an illustration of this. If we have this initial point in one set here, set 2 here. We're going to project that in the first iteration. We're going to project that over to set 1. So this will be using P1 of that point, P1 of x. Then we're going to project that to the closest point in set 2. Now note, importantly, that this is a different point, right? We're going to use projector 2 to project that point that's on the boundary of P1 into P2. And now that is a point that is closer to the intersection and also different from the initial point. So we didn't just undo what we did before. Then we go back to set 1, P1 of x, go back again to set 2, and eventually we'll get to this point right here where we have the solution, which lies in the intersection of the two sets. So for us, these projector functions P1 of x and P2 of x will be defined as DFTing the image to k-space. Sorry, for set 1, that is the set of data, the set of images that correspond to the acquired data. What we'll do is DFT the current estimate of the image to k-space, and then replace the data in the acquired k-space locations with the original data. With the acquired data. And then to go back to an image, we'll take an inverse DFT again to get back to an image. So that is, we'll have projector 1 should take some image which does not quite match, whose data in k-space do not quite match the acquired data. You will DFT it back to k-space, and then in the k-space locations where you have the acquired data, you replace those erroneous points in that image's data with that acquired data, and then you inverse discrete Fourier transform to go back to the image. So that projector is enforcing that those k-space points equal the acquired data. To get to take any image and project it onto the closest image that has phase equal to the low-res estimate, you replace the image with its magnitude times the phase, times the low-res phase. So that is, if you have this image that does not quite match the low-res phase, that has additional phase on top of the low-res phase, you replace it with its magnitude times e to the I angle of the phase of the symmetric region image, which has the same definition as before. Now this is actually not a min-distance projector or a convex set technically, but in practice it actually does work to do this. You do find that you always converge to a better and better solution running this algorithm, even though one of the sets is not actually convex or and doesn't use a min-distance projector. Okay, so taking another view, high-level view, this is the Pox algorithm. We start with this initial point in set 1. That is the data consistent image. So by point, I mean an image. So you can get that very easily, for example, by zero filling. Even though zero filled image is not a good-looking image, its k-space data does exactly correspond to the acquired k-space data. So you start with that, and then you project. So that's something that sits in set 1. Then you project it to set 2, back to set 1, back to set 2, back to set 1, until you have found that it stops changing significantly. So here's a flow graph of the algorithm at a lower level. Note that it's iterative, so it loops back. It keeps looping back over and over again. And that loop back specifically happens right here, right? So you start with an image of zeros, and then you take the original acquired data set, right, where the shaded region, the original acquired data is here. We'll call that, as we have before, we'll call that m sub pk of kx, ky. You replace the acquired region in your initial image with the acquired data in the first step that, again, as I said on the previous slide, would give you a zero-filled reconstruction. Then, so that is this replacement step is the projector 1. And then that gives you your estimate of the image, which we'll call m of kx, ky. The more darkly shaded region here is the part of k-space that's going to be filled in by the algorithm as you go. But at each step, you take the inverse discrete Fourier transform. After filling in the data, you take the inverse discrete Fourier transform. That gives you an image estimate corresponding to your current k-space data estimate. Then you take its magnitude to project it onto the set that has the phase from the low-res region. You take its magnitude, and after taking the symmetric data, and it taking its inverse discrete Fourier transform, you calculate the image, the low-resolution image for phase correction, and so you get, from that you can derive exp of I times magnitude ms of xy, right? So this is a unit magnitude image that has the phase of the low resolution image. You multiply that by the magnitude of the current image estimate. That gives you, so this really is the main step of projector 2, which is getting you the phase consistent data, and then that gives you mxy times e to the, or exponent of I times angle m sub s of xy. So this then corresponds to the phase corrected image data. You take its DFT to go back to k-space, and now it should be filled in all the way. And then you take that segment where you have filled it in, and that segment stays put while you, when you do the next, when you go back to the projector 1 step, when you fill in the missing data, or sorry, when you fill in the acquired data region with the actual acquired data. So this just repeats over and over again, and until the image stops changing significantly. And that is the Pox algorithm.